very good day to the Snow Amalina. Today we are going to discuss about the question. The question is, butane is burned with air and then no carbon monoxide is present in the combustion product. A. Use a degree of freedom analysis to prove that if the percentage excess air and the percentage conversion of butane are specified, the molar composition of the product gas can be determined. And the part B1 is calculate the molar composition of the product gas for each of the following cases. For the case 1 is theoretical air supply, 100% conversion of butane, and the case 2, 20% excess air, 90% conversion of butane. For both cases, I use the molecular species balance method for both questions. And for the case 1, theoretical air supply, 100% conversion of butane, and then we must write the complete combustion of butane equation, which is C4H10 plus 6.5 bracket O2 plus 3.76 N2, and then produces 4 moles of carbon dioxide and 5 moles of water and 24.44 mole of N2, and then 100 mole of the butane is fed as the basis of calculation to the combustion reactor. And this is the flow chart that I have drawn. According to the flow chart, there are 4 unknowns, which is NO mole air, and N1 mole CO2, N2 mole H2O, and then N3 mole of nitrogen. We have 5 independent molecular species balance, which involve butane, oxygen, carbon dioxide, water, and nitrogen. And there is no equations relating unknown variables. So this results in 0 degrees of freedom. So the problem can be solved. Next is I will lay out the molecular balance involving these 5 species. And then, for the first one, C4H10 balance, input goes to consumption. So the consumption of the butane will be 100 mole of C4H10, which is fed to the reactor 1 to combust with air. And then for the O2 balance, is input equals to consumption. We try to find the number of moles of the air fed to the reactor. For the input 1, we multiply NO by 0.21 mole O2 over mole air, and then the consumption will be equal to the 100 mole of C4H10 consumed multiplied by 6.5 mole O2 consumed, and then calculate it. You will get the answer for the NO, which is 3095.24 mole of air. And then for the carbon dioxide balance, generation equals to output. And for the generation, we multiply 100 mole of C4H10 consumed by 4 mole of CO2 generated. So that we will get the value for N1, which is the number of mole of the carbon dioxide. And the answer is 400 moles of CO2. And then for the water balance, generation equals to output. And then to find the value of the N2, we multiply the 100 mole of C4H10 consumed by 5 mole of H2O generated. And you will get the 500 mole of H2O for the value of N2. And then for the nitrogen balance, input equals to output. It is non-reactive species. So there is no generation term or no consumption term in the balance equation. The value of N3 can be found by multiplying the number of mole of the nitrogen in 1 mole of air by 3095.24 mole of air, it is equal to N3. So N3 equals to 2445.24 mole of nitrogen. In order to find the molar composition of each product gas, we have to sum up each mole of product gases, which is the number of mole of the carbon dioxide plus number of mole of water and nitrogen. So the total number of mole of product gases is 3345.24 mole. Find the mole fraction of each product gas. So for example, for the mole fraction of CO2, YCO2 is equal to the number of mole of carbon dioxide divided by the total number of mole of product gas. You will get the value for the mole fraction of the carbon dioxide. And same way goes to the mole fraction of water and mole fraction of N2. In this case 2, 20% SSF, 90% conversion of butane. We use a complete combustion of butane equation as written here. C4H10 plus 1.2 SSF is added to the oxygen, and then times 6.5 bracket O2 plus 3.76 N2 the bracket, and then produces 4 mole of carbon dioxide and 5 mole of water. And then since it reacts with 20% SSA, there will be leftover oxygen at the outlet stream. So in order to find the remaining number of moles of oxygen, we multiply 1.2 SSA times 6.5 reacted minus 6.5 reacted with the butane. So you will get the 1.3 moles of oxygen and 29.328 nitrogen. You will go to the degree of freedom analysis, and in the degree of freedom analysis, there are 6 unknowns which involve the NO, N1, the number of moles of the butane, and N2, the number of moles of the carbon dioxide, N3, the number of moles of water, N4, the number of moles of oxygen, and the number of moles of the nitrogen, N5. And then there is one independent chemical reaction, and next there are 5 independent molecular species balances, which involve the butane, oxygen, carbon dioxide, water, and nitrogen. And then we will have one SSA specification, which relates to the NO to the quantity of the fuel bag. And lastly, we have the one butane conversion specification, which relates to the 90% conversion of butane. And we will carry out the balance for each molecular species. So for the first one, butane balance, input equals to output plus consumption. Since only 90% of butane is converted in the reaction, so the input is 100 mole of the butane fat, and equals to N1, which is the output, plus 90 mole of the C4H10 consumed in 100 mole of C4H10 fat, and then we multiply it by 100 mole of C4H10 fat to get the what is the consumption of the C4H10 here, and then we will get the value for the N1, which is 10 mole of C4H10. And for the carbon dioxide balance, generation equals to output. For the generation 1, 90 mole of the butane is consumed, and then it is multiplied by 4 mole of carbon dioxide generated, which will be equal to the value of N2. So N2 equals to 360 mole of carbon dioxide. And for the water balance, generation equals to output. So the output equals to N3, and then generation will be 90 mole of the butane consumed multiplied by 5 mole of H2o generated. So it will be equal to the 450 mole of H2O. And for the oxygen balance, there will be an input and output and the consumption. And for the input, 0.21 mole of oxygen in 1 mole of air is multiplied by 3714.29 mole of air. So the output will be N4 plus the consumption. 90 mole of C4H10 consumed is multiplied by 6.5 mole of oxygen consumed. And then calculate it. So you will get the value of N4 equals to 195 mole of oxygen gas. And for the nitrogen balance, input will be equal to the output. N5 equals to 0.79 mole of nitrogen times the 3714.29 mole of air, and the N5 will be equal to 2934.29 mole of nitrogen. To find the molar composition of each product gas, we will need to sum up the individual number of moles of product gas. So the total number of moles of product gas will be equal to 3949.29 mole. And then we calculate the mole fraction of each product gas. For the mole fraction of the butane, YC4H10 is equal to the number of mole of butane over number of mole of the product gas, which has been summed up just now. Okay, so you calculate it to get the value of the mole fraction of butane. So it is equal to 0.00253, and then same way goes to calculate the mole fraction of each product gas. I think that's all from me.
Hello, I got a question. For the molar composition, do we need to find the percentage? Like, as you said just now, 0.00253. So do we need to times 100 to find the percentage?
No need, just find the mole fraction. Not the percentage of mole fraction.
I have question. At the chemical reaction before, can we not add nitrogen into the reaction? Just say that the butane react with the oxygen become.
For this case, it is because the butane is reacted with excess air. If the excess air is given, we must add the nitrogen into the combustion equation. Okay, for if it reacts with the oxygen, then we will not put the nitrogen into the complete combustion equation for the butane.
But we can just delete the nitrogen.
Can you guys see my screen?
Yes.
So for atomic species balance method, also have to make a chemical reaction balance, just like what Yong-Sun do just now. It's the same chemical reaction. And then for degree of freedom, we refer to, so for atomic species balance method, we also have to make a flowchart, same as Yong-Sun, but the degree of freedom analysis is not the same. So for atomic species balance method, the degree of freedom analysis is like this. So for unknowns, number of mole of oxygen, number of mole of butane, number of mole of water and number of mole of carbon dioxide. And then we plus the one independent chemical reaction. Then we minus 5 independent molecular species balance. Then we get then we also get 0 degree of freedom. If we get 0 degree of freedom, then we already can solve for the molar composition. Case 1, which is a theoretical air supply, 100% conversion of butane. So first one, we have to calculate the number of mole of oxygen, mole of butane times 6.5 mole of oxygen over 1 mole of butane, then we get 650 mole of oxygen. For moles of air, number of mole of air is equal to 650 mole of oxygen times 1 mole of air over 0.21 mole of oxygen. Then we get 3095.24 mole of air. And then we calculate for the nitrogen, 0.79 mole of nitrogen over 1 mole of air times 3095. Sorry, I forgot to put 24 at the back. Okay. So we get 2445.24 mole of nitrogen. We make the atomic carbon balance, input equal to output. So this one is the left side is for input and the right side is for output. This one we make it based on the flowchart that we make at the beginning of the solution. And then we just 100 mole of butane times 4 mole of carbon atom over 1 mole of butane equal to 0 mole of butane times 4 mole of carbon over 1 mole of butane plus number of mole of carbon dioxide times 1 mole of carbon over 1 mole of carbon dioxide. Then we get number of mole of carbon dioxide is 400 mole. Then we make for hydrogen. It's the same way. Input equal to output, and then we just insert the value here. 100 mole of butane times 10 mole of hydrogen over 1 mole of butane equals to number of mole of water times 2 mole of hydrogen over 1 mole of water. Then we get number of mole of water is 500 mole. Then we calculate for the fractional yield. So first we have to calculate the 3345.24 mole. Then for the fractional yield, we use the same method as the molecular method. So number of mole of carbon dioxide over number of mole of the total of the 3 unknown. Then we get 0.120 for carbon dioxide, 0.731 for nitrogen gas, and then 0.149 for water. So that's all from me.
So for question 2, which is calculate the molar composition of the product gas for each of the following cases: 20% excess air and 90% conversion of butane. So I will be doing the method 2, which is atomic species balance. So first of all, we need to do the equation, which is butane, the complete combustion of butane which is butane, oxygen, nitrogen, carbon, which produces carbon dioxide, water, oxygen, which is the excess air, and the nitrogen. So from this, you will get this simplified equation. Okay. So this is so we are using 100 mole as our basis. For this, we need to start with the degree of freedom analysis, which is different from the molecular species balance. So first we got 6 unknowns, which is N0 mole, the number of mole of air, and then secondly we got butane, carbon dioxide, water, oxygen, and nitrogen. So then we minus 3 atomic balances, which is the element C, H, and O. And then we got 1 nitrogen balance minus with 1 excess air specification, which relates N not to the quantity of fuel fed, and 1 butane conversion specification, which is 90% conversion of butane. So we get 0 degrees of freedom, which means it is solvable. Okay, now we go to theoretical. First we calculate oxygen, which is 100 moles of butane. The number of mole of oxygen, which we use 100 mole butane times with 6.5 moles of oxygen, which you can see from here. 6.5, which is after you've done the balance, mass balance. So times over 1 mole of butane, you get 650 mole oxygen. And for O, number of mole of O, 1 air, 0.21 mole O2 times 650 moles O2 times 1.2, which is the 30% excess air. So you get 3,714.29 mole air. So now the butane combustion, which was 90% conversion of butane, you left with 10% unreacted product. Yes. So N1, 0.1 times 100 mole basis, you get 10. Sorry, here is 10. It's supposed to be 10. Okay. So then we start with carbon atomic balance. So as said by Youngson and Adeline, it is also input equals output. So 100 moles of butane times 4 mole carbon over 1 mole of butane is the input, and the output is 10 moles butane times 4 moles carbon over 1 mole butane, and then plus N2, which is the carbon dioxide, mole CO2 times 1 mole carbon and 1 mole carbon dioxide. So N2, you will get 360 mole CO2. H, the hydrogen atomic valence, 1 input equals output. So 100 mole of butane times 10 mole H, hydrogen, over 1 mole of butane is for the input, and the output is 10 mole butane times 10 mole carbon over 1 mole butane plus N3, which is water, so because you have H here for atomic balance of hydrogen. So N3 mole H2O times 2 mole of H and 1 mole over 1 mole of H2O. So N3, you will get 450 moles of H2O. For all atomic balance, you get from this here NO 3714.29 mole air times with 2 moles O over 1 mole of 2. So equal 350 moles CO2 times 2 mole O over 1 mole CO2 plus 450 mole H2O times 1 mole oxygen over 1 mole H2O plus N4 mole oxygen, O2 times 2 moles of O over 1 mole of oxygen, you will get N for 195 mole O2. And N atomic balance, which is nitrogen, N5, we just times 0.79 moles, N2 times with 3714.29 mole air, and you will get your answer, which is 2934.29 moles nitrogen. So to the total number of moles of product gases, which is NT and N1 plus N2 and plus N3 plus N4 plus N5. So you get the total of 3949.29 moles. So to count the chart, so you need to N1 over N total. So you get as mentioned above. So do you have any question?
No question.
I think no questions for me.
Okay.
So now I'm using the molecular species balance. So first URF analysis. So we have 4 unknown variables here, which is CO2, H2O, and N2, and so the excess air. So we have one independent chemical balances, which is this. I didn't include the N2 because assume the excess air is 100%. This is actually 5 actually. And this is 0 because the question didn't specify the percentage of excess air. Okay, so this I'm going to find the mole of oxygen theoretically from 100 mole of C4H10. You can use ratio 6.5 or here on the chemical balance to 1 mole C4H10 here. So we can just ratio it out, can find the mole of oxygen. Here is same thing, can find the same mole of air theoretically. 1 mole of air, we know that has 0.21 percentage of O2 in excess air. You can just multiply it by 650 mole. So we get 3095.4 mole of air. So firstly, I'm going to find the mole of CO2, which is N1. So this is generation to output because we don't have any input in CO2 and also we don't have suction. So we can just ratio it out. 650 mole O2, we found it here. Can just show it, divide by 4 mole of CO2, which is from chemical balance here. So 13 of 4 mole of O2 cancel out this O2. So we got this 400 mole of CO2. Next is the H2o generation equals to output. So we don't have any input and consumption. So we can just ratio it 400 mole of CO2 times 5 mole of H2O from the chemical balance divided by 4 mole CO2, so from the chemical balance. So we can cancel it out small 500 mole of H2O. Okay, the lastly is N2, nitrogen. Nitrogen is not really reactive it's not really dissipate in the chemical reaction. So we can just input the output. It's straightforward question. can just multiply it by 0.79 divided by mole of air, multiply by the mole of air, because we have 0.79 mole nitrogen in our air, excess air. So this is my mole of nitrogen. So the question wants the molar position, which is also called as molar fraction. So formula of molar fraction is just number of mole of the specific reactant over total reactant. Okay. So CO2 small is 400 and below is 400. Just total up everything. H2o, N2, and CO2 is 0.1196. This is also the same thing. H2o 500 mole divided by total reactants mole, which is 400 plus 500 is 2445. Same as nitrogen. The mole of nitrogen is 2005 divided by total. It's 400, 500, 445.2396, which is equal to 0.780. So that's all from me.
Okay, first, I will explain the part 2 using extend reaction method. So from the question, we know that the flowchart is like this. And the degree of freedom from the flowchart, we know that we have 6 unknown variables that what we must find, and there are 4 independent reactive species in this reaction, which is the butane, oxygen, carbon dioxide, and the water. And there are 1 independent non-reactive species, which is the nitrogen, and 1 butane combustion specification, and 1 excess A specification, which is the 20% excess of A. And there are 1 independent reaction, which is the reaction involved in this question. So first, we must find the number of mole of the excess A. First, we multiply the number of mole of the butane with the how many mole of oxygen generate using the number of mole of the butane, which is 100 mole of the butane multiplied by 6.5 equal with the 13 divided with 2 mole of O2, and we get 650 mole of oxygen. In the question also mentioned there are 20% excess of A involved. So 100% plus with 20% divided by 100, and we will get 1.2 excess of A. So when we calculate everything, we will get 3,714.29 mole of it A involved in reaction. The question also mentioned that there are 90% of combustion of butane involved. And from this, we know that there are 10% of butane unreacted in this reaction. So from this, we can directly calculate the number of mole of the butane at the output side, 100 mole of butane at the input side multiplied by 0.1, which is how many butane unreacted in this reaction. So we get 10 mole of butane at the output side. So this is the reaction involved in the one correction in this. So I forgot to put the nitrogen species. So for information, how we want to use extent of reaction method to calculate. So if the species at the product side, we consider it as positive, and if the species at the reactant side, we consider it as negative, and if the species is inert gas, we just consider it as 0. So first, to find the number of mole of the nitrogen, which is non-reactive species and also known as the inert gas, we just the number of mole of the final, which is the output nitrogen, to the number of mole of the nitrogen at the output side, at the input side, plus 0, which is the inert gas, and we get the number of mole of nitrogen. So next, we can find the number of mole of the water, which is the number of mole of water at the output side, which what we must find equal to the number of mole of the water at the input side, which is equal to 0 because water as a product in this reaction, as we can see at the reaction, plus with the 5 extent of reaction. Because this question just contain one reaction, so we call the reaction as the extent of reaction 1. So why we plus with 5 extent of reaction 1? Because the water is at the product side. So as we know, when the species at the product side, we consider it as positive. So we get 5 extent of reaction for the number of mole of water. Then to find the number of mole of CO2, we also use the same method as H2O, which is the number of mole of carbon dioxide is equal to the 4 extent of reaction. So from the calculation above, to find both number of mole, we must know what is the extent of reaction. So as mentioned at the question, there are unreacted butane that we can use to find the extent of reaction. So the number of mole of the butane at the output side, which we find here, equal to the number of mole of the butane at the input side minus extent of reaction 1 because the butane is at the reactant side. So we get the extent of reaction 1 is 90 mole. So after we get the extent of reaction 1 value, we can insert it into the equation 1 and insert it to the equation 2. So we can find both number of mole. And the number of mole of N2, so we use the same method, same way as we find the number of mole of water and number of mole of carbon dioxide. For the molar composition, we use the same method as how we find in atomic species method and molecular species method, which is the number of mole of the species divided by the number mole of total, and we get the molar of composition of each composition of feed gas. Okay, that's all from me. Thank you.